The James Webb Space Telescope has now produced another image that suggests something is seriously wrong with our universe. Either our space is behaving in ways we do not understand, possibly hinting at some form of intelligence, or our scientists have fundamentally misunderstood it. Since the launch of this powerful new telescope, the scientific world has experienced a crisis unlike anything before. It seems as though these new findings are trying to tell us something urgent, but so far scientists are engaged in more arguments than they are in presenting us with real new facts and truths. Could this signify the end of everything we know? No stone has been left unturned since the James Webb Space Telescope, JWST, revealed images of galaxies that are so old and so perfect that they shouldn't even exist. This was the beginning of a drama in modern science that continues today. More and more images show even crazier phenomena and impossibilities. Nothing in the young universe seems to be behaving the way scientists had thought it would, and now it is becoming clear that the entire universe is not what our scientists once believed. Until now, researchers have assumed that the universe is homogeneous, meaning the nature of the cosmos. The idea of a homogeneous universe dates back to early 20th century cosmology. Albert Einstein introduced the cosmological constant in his general theory of relativity, describing a static universe that neither expands nor contracts. Shortly after, it became clear that we do not live in a static universe but rather in one that is highly dynamic, with every phenomenon in constant motion. The physicist Alexander Friedmann concluded that Einstein's field equations could also describe an expanding or contracting universe. Georges Lemaitre then proposed the Big Bang theory, suggesting the universe expanded from a single point. These ideas led to the concept of a homogeneous and isotropic universe, which is now anchored in the so-called cosmological principle. The principle states that the universe is homogeneous and isotropic on large scales, meaning it looks the same in every direction regardless of where you are. Let's compare this to a landscape. A homogeneous and isotropic landscape would resemble a vast, endless desert in which the sand is evenly distributed everywhere, and there are no hills, valleys, or other geographical features. No matter where you go or which direction you look, the landscape looks the same. Similarly, in a homogeneous and isotropic universe, stars, galaxies, cosmic nebulae, and other phenomena would be roughly evenly distributed in space. However, recent discoveries made by the James Webb Space Telescope and other astronomical observations suggest the universe may not be as homogeneous and isotropic as once believed. It may be strange to imagine the entire universe as a landscape, but this analogy is not far-fetched. The dimensions are simply much larger. Galaxies with millions or billions of stars wander the universe along filaments, coming together in groups. We are aware of gigantic empty spaces or voids, black holes, and other phenomena that all play a role in the cosmic spectacle. Researchers have now discovered that one side of the sky contains about 0.5% more quasars than the other side. Quasars are extremely bright galactic nuclei powered by supermassive black holes. This uneven distribution suggests that matter in the universe may not be evenly distributed after all. Another discovery that challenges the theory of a homogeneous and isotropic universe involves two extremely large cosmic structures, the Big Ring and the Giant Arc. These structures, formed by galaxies and galaxy clusters, are so large that they surpass the scale on which the universe is supposed to be homogeneous and isotropic. Essentially, they are so vast that our measurement techniques fail to capture them accurately. Such megastructures indicate the existence of cosmic mountains within the landscape of the universe, and no one yet understands how they fit into the universe's overall structure. These are just the latest discoveries reinforcing the suspicion of an inhomogeneous universe. Earlier evidence also pointed in this direction, including the different expansion rates of the universe. Different methods of measuring the universe's expansion have yielded inconsistent results, a phenomenon known as the Hubble tension. If the universe is not the same everywhere, this could explain why it does not expand uniformly. Somewhere between the cosmic background radiation and the redshifts, there might be a previously unknown layer of the universe or force responsible for the discrepancies in measurements. Alternatively, the universe might not be expanding uniformly because there are cosmic mountains obstructing its path. The James Webb Space Telescope has contributed to this research, confirming the existence of the Hubble tension. But why does the cosmic background radiation show an even distribution of matter? When we look at the cosmic background radiation, CMB, it indeed reveals a uniform distribution of matter. The CMB is considered the afterglow of the Big Bang and is essentially uniform microwave radiation. This radiation originated around 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms in a process known as recombination. Before recombination, the universe was a hot, dense plasma of ions and electrons that constantly collided and scattered photons. These constant collisions ensured that matter and radiation were tightly coupled and in thermodynamic equilibrium. As the universe expanded and cooled, the temperature dropped below 3000 Kelvin, allowing electrons to combine with protons, forming neutral hydrogen. This drastically reduced the number of free electrons, making the universe transparent to photons, which could finally travel unhindered, giving rise to the cosmic background radiation we observe today. This uniform distribution of CMB radiation initially led scientists to believe the universe was almost homogeneous and isotropic. But now, imagine the universe isn't expanding into an empty void, but into a space where something already exists. The Big Bang and the distribution of matter shortly thereafter may have been homogeneous, but as the universe expanded, it could have encountered obstacles that disrupted its homogeneity. These obstacles could be numerous, leading to fantastic theories that thrill space enthusiasts but confound scientists. According to old theories, space itself came into existence with the Big Bang, and the expanding universe is essentially that space. However, quantum physics has already demonstrated that nothingness cannot exist. It has also shown that a multiverse with many nested dimensions and countless universes of various shapes, sizes, and natures is more plausible than the idea of a single universe. So what if our universe is expanding into a space containing other universes, dimensions, or previously unknown structures? This would imply that our universe is encountering obstacles as it expands, other universes or dimensions that either get in the way or exert resistance on our universe. In this scenario, an initially homogeneous Big Bang could become inhomogeneous as a result of these encounters. Such considerations are exciting, though they receive little official attention despite the many inconsistencies in current astrophysics. Some courageous researchers who support theories like the multiverse have drawn an interesting comparison. Our Earth also began as a homogeneous world. Planets in their early stages are simply collections of gas and dust, just like early stars. Then over time, they develop into more independent heterogeneous entities, taking on individual shapes, wandering within solar systems, colliding with other celestial bodies, and undergoing change. In the beginning, Earth was a glowing hot ball with matter evenly distributed. However, over time, a heterogeneous structure developed, at least on the surface. We now have large oceans and land masses that are not evenly distributed but instead appear randomly. The Pacific Ocean is vast, just as the Eurasian continent is enormous. Africa is nearly adjacent, while the American continents are long and slender. We also observe a variety of structures within the oceans and on land: deep-sea trenches, shallow sections, deserts, high mountains, heavily populated areas, and sparsely populated regions. This inhomogeneity on Earth offers lessons for understanding the universe. Earth, like other rocky planets, has evolved from a homogeneous body to a heterogeneous one. Mars, Venus, and Mercury all exhibit some degree of heterogeneous structure, although not as extreme as Earth's. Meanwhile, the gas giants in our solar system remain relatively homogeneous, having likely changed little over millions of years. The diversity of planets within the solar system reflects the uneven distribution of matter and gas. Returning to the landscape of the universe, it's conceivable that the cosmos too might develop heterogeneous features over time. We must come to terms with the idea that our universe is even more dynamic than we had previously thought. The latest discoveries made by the James Webb Space Telescope have shown that much of our science was wrong in many respects. The old cosmology is crumbling, and we may now have to acknowledge that even physical forces evolve.